Hello everyone, welcome back. Today we'll be taking a bit of a look at natural numbers and piano axioms. Well, what is a number? Let me try to be more specific. Well, how would you define the number three, for example? Try to pause the video and try to just define it without using the word number. Well, there's one way to define it. We can use three fingers and say that those that represent three. That's how you define three. But that's a pretty unsatisfactory and is more or less like a circular argument. You're basically using the number three to define three. So we can't start doing calculus on such a weak definition and foundation. We need much more rigorous definitions and firmer foundations on what a number means before we start doing calculus and analysis on those numbers. Luckily for us, people had the same issue and problem centuries ago. So after years and years of work, Italian guy called Peano came up with some axioms in order to define the set of natural numbers. Now, axioms is just a fancy word. It basically means ground zero. It means we can't really prove them. We start with the axioms. We assume them to be true. So now let's take a look at what axioms really mean. So Peano defined axioms using four definitions. So take this as the set of natural numbers. So the first axiom said that 1 is always part of the natural numbers. The second axiom said that if n is an element of the natural numbers, the successor of n is not equal to 1. So before we dig into what that means, let's look at what the successor means. So successor, capital S basically means successor or next element. So for example, the successor of 2 will be 3, the successor of 4 will be 5, the successor of 1 will be 2, and the successor of 999 will be 1000. So Peano said that there's no element such that the successor of there's no element n such that its successor is equal to 1. So 1 is our starting point. So the third axiom said that if m and n are part of the natural numbers, then the successor of n is not equal to the successor of m. So take for example 2 and 3. 2 the successor 2 and 3. The successor of 2 is equal to 3, but it's not equal to the successor of 3, which is equal to 4. Then let's look at the fourth axiom. Is let k be any subset of the natural numbers. Then k has two properties. Firstly, 1 is a part of k. Then secondly, whenever n is a part of k, then the successor of n, the next element of n, is also part of k. So remember that these Peano's axioms are really important because they define the natural numbers, and the natural numbers are then used to construct the integers, which are then used to construct the rational numbers, which are then used to construct the real numbers, which we'll use to do our analysis on. So these are basically the foundations to our number system. So now let's look at how addition was defined, or how addition is defined using Peano's axioms. So firstly, the first property of addition is if n plus 1 is equal to the successor of n. Well, this is pretty trivial. For example, 2 plus 1 is equal to the successor of 2, which is 3. Right, now let's look at the second property. N plus successor of m is equal to the successor of n plus m. So for example, 2 plus successor of 1 is equal to the successor of 2 plus 1, which in turn is the successor of, remember that 2 plus 1 from the first property of definition, n plus 1 is successor of n, so 2 plus 1 is the successor of 2, and the successor of 2 is 3, the successor of 3 is 4. So that's how we define addition, and that's how we add natural numbers. Well, now let's take a look at multiplication and how to define multiplication. The first property of multiplication says m dot 1 is equals to m. Well, that's pretty simple. Let's take a look at 2 dot 1 is equal to 2. The second property of multiplication says that m dot successor of n equals to mn plus m. For example, let's take a look at how 2 dot successor of 1 is equals to 2 dot 1 plus 2. Right, now let's take a look at how to prove one of the problems using Peano's definition of multiplication. Right, let's see how to prove 3 dot 2. Let's see how we can prove that. We know that it is equal to 6, but we can't use that because the only definitions we have is m dot 1 equals to m, and this is clearly not 3 dot 1. If it was 3 dot 1, it would be equal to 3, but we don't know what 3 dot 2 equals to. All we know is m dot successor of n equals to mn plus m, and m dot 1 equals to m. So let's see how we can break this down to the definition and how we can prove that. So remember that 3 dot 2 is equal to 3 dot successor of 1. Well, because successor 2 is equal to the successor of 1, so we can replace 2 with successor of 1. Next, we can write it as 3 dot 1 plus 3. This is from the second definition of multiplication, where we take 3 as m and 1 as n, and that's how we get 3 dot 1 plus 3. Next we get, remember 3 dot 1 is equal to 3, so m dot 1 equals to m, so 3 dot 1 equals to 3. Next we get 3 plus 3. Well, we don't know how to do 3 plus 3 either. We know it is 6, but we really don't know how to do it using Peano's, or using the definitions of addition and the definition of multiplication, because we haven't proved any of the associativity, commutativity, or the distributivity of the natural numbers. So we can only rely on the two definitions of additions and the two definitions of multiplications to compute this. So let's see how we can go about this. So we can write 3 plus 3 as 3 plus the successor of 2. And we can further break this down into 3 plus 2 plus 1. Remember this from the definition of addition, which says n plus 1 equals successor of n. So the successor of 2 is equal to 2 plus 1. So that's how we get here. Next, we can write 2 as the successor of 1. 3 plus successor of 1 plus 1, just as we did in the first step right over here. Well, how about now we can write this as a successor of 3 plus 1 plus 1. How do we get here? We get here from the addition definition of addition, which says m plus n equals to successor of m plus n. So that's how we get to this step. Next we can write 3 plus 1 as the successor of 3. So this is also from the definition of addition, where n plus 1 is equal to the successor of n, so 3 plus 1 is equal to the successor of 3. And we know that the successor of 3 is 4, so we can write it as 4 plus 1. Now we can further write this as from this definition, where from this definition we can, from the second definition of addition, we can write this as successor of 4 plus 1, which is equal to the successor of 5, which is then equal to 6. So that is how we compute 3.2 using the basic fundamental addition rules of addition and multiplication. So I hope you can see that what we take for granted and what we take as pretty trivial wasn't really pretty trivial or easy back then, maybe in the 18th century or the 17th century. So this is the foundations of our number system. So in the next video we'll prove the commutativity, associativity and distributivity of natural numbers. See you next time.